it's very easy to do the square root function if you just look at it as x to the 1/2 and do the standard rule. But I want to show you another approach that's related more to how do you find the derivative of the inverse of any arbitrary function. Now, this result right here states that if you compose a function with its inverse, you always get x back. And that's the simple example there is if f of x is x squared and f inverse is the square root of x, well, squaring the square root of x gives you x back. And this is just a general truth for any function and its inverse. If you compose a function with its inverse, you're going to get x back. Now, you could go in the other directions too. In fact, that's listed as part of the definition. F inverse evaluated at f of x is also equal to x. And those two are always true. Sometimes there's domain things, like, for example, for x squared to have an inverse, it needs to be defined on the interval 0 to infinity, so the function will be 1 to 1. But in any event, a lot of times the domains and ranges just kind of get left out because formally the proof goes the same way. Now, so what we do right here, this is the composition of two functions. It's a composition of two functions, namely the function and its inverse. So that means you can apply the chain rule. So ddx of that expression, taking the derivative of x is easy. You see that right over here, right? But the chain rule says you take the derivative of the outer function, which is f, you evaluate it at the inner function, then you take the derivative of the inner function again. Now notice I kind of, in an uncivilized sort of way, mixed the notation here. I used ddx to denote f prime at f inverse because it just seemed awkward to try to put a prime with this notational scheme. So again, I called f prime because it was easy, but I just wrote down the derivative of f inverse of x using the Leibniz notation. All right, now from here we are trying to get the derivative of the inverse function in terms of the derivative of the parent function, and that's exactly what happens if you divide through by f prime at f inverse of x, is what I did right here. So what we get is ddx of f inverse of x is equal to 1 over f prime evaluated at the inverse function. All right, that happens every time. This is extremely useful when you're trying to find the derivatives of the inverse trig functions, but it works for absolutely any function. So I used a real simple example here for you. Let's assume that the parent function, if you want to call it that, is x squared. And it's certainly the inverse of the square root of x. Its derivative is 2x. And notice that just here it is in all its splendor. If you look at this left-hand side, the root x would be the square root the inverse function that you would see right here. That square root of x is the inverse function. Well, it's 1 over the derivative evaluated at the inverse function. Well, that would be 2x, and it would go downstairs based on this form right here. Now, I hope this color coding helped you a little bit, the green here and the green here. But that's kind of neat. All these years, I've sat through a few calculus classes and observed a few calculus classes, and it doesn't seem like this gets taught that much. Everybody just develops all the rules of differentiation in an ad hoc sort of way, not necessarily ad hoc, but this is a very powerful result. It applies to any function and its inverse. Now, I have a practice problem for you here. If you want to make a comment, it makes it very easy to find the derivative of the natural log of x. So see if you can use that result. I'm not sure what they even call it. I think it's the inverse function rule or whatever, but it's what it does is it relates the derivative of the inverse function to the derivative of the parent function. Okay, hope you guys enjoyed that.